Hi, my name is Mr. Turner, and if you do not know me, I also teach Algebra 1 here at Central High School. I'll be doing a lot of the homework videos for the Algebra 1 curriculum this year. If you ever have a question, I'm in room 212. Well, basically, this is our first assignment, and one of our main objectives in this first assignment is to understand how to identify independent versus dependent variables. So we're going to be looking at some scenarios. We're also going to be trying to figure out which graph corresponds with which scenario, and just some basic labeling on the X and Y axis. So let's jump into it. So this is what your page looks like as soon as you look at it. At the very top, it says practice. We're going to read each scenario, identify independent and dependent quantities, in the question. And then we're also going to look for each graph that corresponds A through F. D, E, and F are on the next page. If you don't see them, just flip over, and we'll be using those as well to figure out which of these scenarios go with which 6 of these graphs. And we're also going to do some labeling, like I said, on the X and Y axis, just to make sure that we understand how that all works. So we're going to look at 2 of them together in this video, and for the rest of the assignment, you need to go and look at the other 4 scenarios and match the other 4 graphs in the same way that I demonstrate here. So let's look at question 1A, which is called Endangered Species. I'm going to read it. The Elkwood Aquatic Society is working with various reptile species to increase their populations. The initial population of 450 endangered turtles tripled each year for the past 5 years. So I'm kind of thinking a few key words in here. We're talking about turtle population. It seems like it is tripling each year. That seems important. Based on the context of the question, their goal is to increase their populations over time. So one of the main things that we want to look at these graphs is we want to think about, are they going up over time? Are they going down over time? Is it a little bit of each? Does it ever flatten out and stay the same over time? So which of these graphs to you, A through F, seem to increase starting at some initial place on the graph and just continues to go up over time? So A seems to do a little bit of both. It seems like it goes up and then down. B does seem to be going up over time. That's pretty good. Kind of a constant rate of change here. C is going down with a constant rate of change. And then D, it's going up, but it really kind of has multiple levels. At the beginning, it's increasing rapidly. It kind of levels off, which there's no change there, and then it goes back up. And E and F seem similar. They both seem to curve instead of be more of a line, but one seems to be increasing and one seems to be decreasing. So I want you to think which of those best seems to follow the storyline. So out of all of those, I think the best one would be E. If you chose E for that, then you did very well. So why do we think it's E? Well, first of all, it is increasing the entire time. And if you think about the idea of tripling, for example, let's say I didn't start at a number like 450. That number is fairly large. Let's say you start at the number 5. Well, if I only had 5 turtles and then I triple it, well, that now goes to 15. Well, then I triple that. The next year, that's now at 45. And so, from 5 to 15, I only really increased by 10. But that second time, from 15 to 45, it really increased by like 30. So that's why I don't necessarily want to pick one that goes up in a line, because that seems to me be more going up by the same amount every time. But when you triple something or quadruple or double, really the distance is going to get further and further away from your initial value rather quickly. So let's think, we got to know our labels here. So that first label I think we'll go with is endangered species. Thought that was going to work really well. Let's try that again. Endangered species. So let's title it. And then we have a few other things that we want to kind of think about. We wanted to think about what is the independent and what are the dependent variables. So if you remember, What makes something independent versus dependent? When one quantity depends on another, that's what makes it the dependent quantity. So what depends on what in this scenario? Well, the time really determines the population. So we have on the bottom, what I would argue is over time, your population will change, and based on how long of a time period goes by, that will ultimately tell you the population. So we definitely want to identify population as the dependent variable. And we want to kind of think of the time in years as the independent variable. Okay? Now, there's one other thing we want to kind of label. There's not too much labeling that you can do here, but there's one very important number that they gave you, 450, and that's the initial population. So we may think about throwing 450 right there just so that we can understand, hey, that was the initial population, but as time goes by, that's the number that's going to triple over time. Let's look at another scenario. So part B says video games is the topic. And Jillian is playing video games at an arcade. Jillian starts with $40 and is playing games that cost 50 cents per game. So we're going to have to kind of think back at all these different scenarios and these graphs and try to see which one goes with which. So as I'm thinking about the story, it sounds like he starts with 40, but if you've ever been to an arcade, that money's going to go up or down. Think about it. It's going to go down. You're spending money per game. So the first time you use 50 cents, you're now down to $39.50. You play another game, you're down to $39. You play another game, $38.50, and so forth and so forth. Every game costs the same, and eventually you're not going to have any money left. So this really seems like a decreasing situation. So I see in A some increasing and some decreasing. I don't really like that it went up before it went down. It also seems to start at 0, which we know we started up a little bit from that. We started at like 40. So even though there's no numbers on these axes, we can know for sure that that's kind of problematic, that it started at 0. Now B, I'm not making money every time I play a game, so that doesn't really make sense. C, okay, maybe you're starting up with some money, and over time you're spending money at a regular rate. I'm kind of digging that one. D and E, again, they both seem to be increasing, so that doesn't really go with the story. So it's really between C and F. Both of these seem to start at a larger value that you initially had, $40, and then over time you're going down. So should it be a line? Should it be linear? Or should it be more of a curve? And so you have to ask yourself, is the cost the same every time? Yes. So for this one, we definitely want to look at C because you're starting up here, your initial value, but every time you play a game, you're losing that same amount. It's not dividing or tripling. That's what would make a curve. So let's kind of look at some of the axes that we may want to label. First of all, this whole thing is about video games. You kind of want to know what the story's about. Let's label the independent variable. So what do you think the independent variable is? So you have to think about what depends on what in the story. And so the number of games I play really determines how much money I have in my pocket. And so what am I in control of? I'm in control of how many games I play. So, number of games played, that seems like a reasonable independent variable. And if I think about the other one, the dependent variable, well, the number of games I play really determines how much money I have left over. And so that can be our axis. So independent, dependent, number of games, independent, money left over, dependent. Okay? So I want you to try those other 4 on your own and just look through each of those graphs and figure out which one goes with which scenario and then label those graphs appropriately. Number 2, compare each pair of graphs and describe any similarities and differences you notice. So I'm going to let you kind of work on this on your own, but I want you to look at A and B And we're going to look at each graph like from left to right. So in terms of graphs A and A, the one on the left, one on the right, what do they have that's similar? And what do they have that's different? And this can be really open-ended. You don't have to necessarily use the right vocab. That's all coming later. And then the next thing I want you to do is look at graphs B. And in B, I want you to think about, well, what do those two graphs have in common? And what do they have that's different? And again, just write those between them, similarities, and then differences out here on the right. Okay. So this last section, this review section, it's not a review of what we've done today. It's more of a review of ideas from the past, maybe a previous course. And if you haven't seen those previous ideas, well, then we're definitely going to work on it some more over the next few weeks, months, whatever. So the first one says solve the equation. So solve means your ultimate goal is to figure out the value of x that makes both sides equal. And so we're going to try to move all these terms around so that ultimately all of the variables of x are on one side and all of the numbers that do not have x are on the other side, and it'll tell us what the value of x is. Now you can do this in a lot of different ways, but you must understand opposite operations. For example, the opposite of adding is subtracting. And the opposite of multiplication, that'd be division. So when you're moving things across an equal sign, really important to understand opposite operations. So I'm looking for like terms here. For example, these are like terms. They both have x as the variable. Or maybe these are like terms because both of them do not have a variable. And so ultimately I'm trying to put these numbers together. However, they're on opposite sides of the equal sign. So what is the opposite of this subtraction symbol? Well, the opposite of subtraction would be addition. So if I want to move that term to the other side, I need to add 3x from the right to the left. That will allow me to put together like terms on the left, negative 2 plus 3, which is positive 1. You could put 1x, but putting x by itself is the same as 1x. And then I'm going to drop the 8, drop my equals. This is canceled out. It's moved to the other side, and now I have 14. So the next thing I want to do is those other like terms of 8 and 14, well, they need to go together. And similar in the first step, what is the opposite of addition? Subtraction. So if I want to move that number over, I need to think 14 minus 8, which is 6. 6 plus 8 is 14. So what I want to do here is I want to check my work, and I want that to kind of lend us into the idea of evaluating, which is what number 2 is. If number 6 is correct, that means that if I replace x with 6 in the problem, for example, negative 2 multiply 6 plus 8, negative 2 times 6 is negative 12, and if you add 8 to that, you get negative 4. Okay? But similarly, on the right side, negative 3x, or negative 3 times 6 plus 14, negative 3 times 6 is negative 18, and if you add 14, again, you get negative 4. So what that means is x equals 6 is a very special value because it makes the left side equal the right side. And this can become very useful in math to know when things are equivalent or when two prices are the same. Maybe it's 2 pizzas or 2 shirts or whatever. But that's what this second question is kind of asking us. X equals negative 2, y equals 5, and then we just have an expression. We just need to plug in the values of negative 2 squared, not x squared, but negative 2 squared, and then negative 3y, that really means multiplication of negative 3 times the value of y, which is 5. So negative 2 squared, a lot of students mess this up, but when you square something, you mean it's multiplied times itself. Negative 2 multiply negative 2, positive 4. Negative 3 multiply positive 5, that's a negative times a positive, so that's negative 15. And then we add 12 to that. So now my goal is just to add 4 minus 15 plus 12. What does all that put together? And honestly, I like to put together things that are easy first, like 4 plus 12, that's 16. And if you go ahead and subtract 15, you get 1. And now we have evaluated that expression for those values. I hope this